Example, consider the linear programming problem. Maximize z equals to 3x1 plus 2x2 subject to the constraints x1 plus x2 is less than equal to 4 and x1 minus x2 is less than equal to 2 and x1 and x2 greater than equal to 0. Solution. Step 1. First we observe whether all the right side constants of the constraints are non-negative. If not, it can be changed into the positive value on multiplying the both sides of the constraints by -1. In this example, all the bi's of the right hand side of the constants are already positive. Step 2. Next, converting the inequality of the constraints to equations by introducing the non-negative slack or surplus variables. The coefficients of slack or surplus variables are always taken 0 in the objective function. In this example, all the inequalities of the constraints being less than equal to, so only slack variable s1 and s2 are needed. Therefore, the given problem now becomes maximize z equals to 3x1 plus 2x2 plus 0s1 plus 0s2 subject to the constraints x1 plus x2 plus s1 equal to 4, x1 minus x2 plus s2 equal to 2, x1 x2 s1 s2 is greater than equal to 0. Step 3. Now represent the constraints equations in matrix form. 1 1 1 0 1 minus 1 0 1 into matrix column matrix x1 x2 s1 and s2 equal to column matrix 4 and 2. The step 4. Constructing the starting simplex table using notations. It should be remembered that the values of non-basic variables are always 0 at each iteration, so x1 equal to x2 equal to 0. Here the column xb gives the values of basic variable as indicated in the first column, so s1 equal to 4 and s2 equal to 2. The complete starting basic feasible solution can be immediately read as s1 equal to 4, s2 equal to 2 and x1 equal to 0 and x2 equal to 0, and the value of the objective function is 0. Starting simplex table cj 3200, basic variables s2 cb 00, xb 42, x1 1 1 x2 1 minus 1 x3 s1 beta 1 equal to 1 and 0, x4 s2 beta 2 0 1. Basis matrix minimum ratio xb upon xk for xk greater than 0 to be computed in the next step. Z equal to cb in xb, delta 1 is minus 3, delta 2 is minus 2, delta 3 is 0 and delta 4 is 0. Delta j equals to zj minus cj equal to cb into xj minus cj. Step 5. Now proceed to test the basic feasible solution for the optimality by rules of given below. This is done in computing the net evaluation of delta j's for each variable xj column vector xj by the formula delta j equals to zj minus cj equals to cb xj minus cj. Thus we get delta 1 cbx1 minus c1 equal to 0 0 into 1 1 minus 3 equals to 0 into 1 plus 0 into 1 minus 3 equals to minus 3. Delta 2 cbx2 minus c2 equals to 0 0 into 1 minus 1 minus 2 equals to 0 into 1 minus 0 into 1 minus 2 equal to minus 2. Delta 3 cbx3 minus c3 equal to 0 0 into 1 and 0 minus 0 equal to 0 into 1 plus 0 into 0 minus 0 equal to 0. Similarly, delta 4 equal to 0. Optimality test. First, if all the delta j zj minus cj is greater than equal to 0, the solution under this test will be optimal. Alternatively, optimal solutions will exist if any of the non-basic delta j is also 0. Second, if at least one of delta j is negative and the solution under the test is not optimal, then proceed to improve the solution in the next step. Third, if the corresponding to any of the negative delta j, all the elements of the column xj are negative or 0 less than equal to 0, then the solution under this test will be unbounded. Applying these rules for the test of the optimality of starting basic feasible solutions, it can be observed that delta 1 and delta 2 both are negative. Hence, we have to proceed to improve this solution in step 6. In order to improve this basic feasible solution, the vector entering the basis matrix and the vector to be removed from the basis matrix are determined by the following rules. Such a vector are usually named as incoming vector or outgoing vector respectively. Incoming vector, the incoming vector xk is always selected corresponding to the most negative value of delta j, say delta k. Here delta k equal to minimum of delta 1 and delta 2 equal to minimum of minus 3 and minus 2 equals to minus 3 equal to delta 1. Therefore, k equal to 1. Hence, the column vector x1 must enter the basis matrix. The column x1 is marked by the upward arrow outgoing vector. The outgoing vector br is selected corresponding to the minimum ratio of the elements of xb by corresponding positive elements of predetermined incoming vector xk. This rule is called as the minimum ratio rule. In the mathematical form, this rule can be written as xbr upon xrk equals to minimum i's xbr upon xik and xik is greater than 0. For k equals to 1, xbr upon xr1 equal to minimum of xb1 upon x1 1 and xb2 upon x2 1 equal to minimum of 4 upon 1 and 2 upon 1, or xbr upon xr1 equal to 2 upon 1 and xb2 upon x2 1. Rest of the question we will do in the next video.